Good afternoon, everybody. We're going to talk about the first week of our analysis of an unknown acid lab. We'll be starting this lab this week and finishing up next week. It's a two-part lab. So again, please just send me one comprehensive lab report from the 2 weeks of this particular lab experiment. All right, what we're going to study in this 2 weeks are acid-base reactions. And what we're really going to be performing, well, actually, you won't be performing any of these things. But you'll get to, what is that noise? But you'll get to, at some point in the future, what we're going to be doing are what we call titrations. And more specifically, we're going to be doing acid-base titrations. Wonderful. What is a titration? A titration is essentially just a careful way of doing a chemical reaction. And we use titrations to determine unknown concentrations of things, among some other subtleties. What we're specifically going to be doing are acid-base titrations. So we're going to be really carefully studying acid-base reactions to determine unknown concentrations of things. We will also use a titration in week 2 to figure out the identity of an unknown acid. All right, so let's talk about what we're going to do in week 1 of this experiment. So in week 1, let me just draw this glassware really quickly. We're going to be using a burette for all of our titrations. So you've used burettes at some point in the past, and actually we used them in Gen Chem 1 really early on. A burette is just a device where we have a little stopcock so we can slowly add our liquid from this burette to an Erlenmeyer flask down here. Just a little vocabulary. What we have in the burette is called the titrant. For week 1, actually for both weeks, our titrant is going to be some solution of sodium hydroxide, and this is an aqueous solution. All right, so we're going to be adding our titrant from our burette. Again, the point of your burette is so we can accurately measure the volume of our titrant that's dispensed. So you might remember these burettes are marked, are graduated every 1/10 of a milliliter. So we should be recording significant figures to the 100th of a milliliter. Okay, we are going to add our titrant to our analyte. In this case, this is the solution that contains an analyte, a compound of interest in this case. So our analyte in this case is going to be a solution of KHP. So KHP is not a formula, it's an acronym. It is a weak monoprotic acid. Let's just call it HA. As you know, all weak monoprotic acids have a proton that they can donate in water. All right, so what we're going to be studying is this reaction between a strong acid, sodium hydroxide, and a weak, let me say that again. We're going to be studying a reaction between a strong base, sodium hydroxide, and a weak acid, KHP. All right, the goal of the first week of this experiment is to use this titration to determine the concentration, the unknown concentration of sodium hydroxide. So we want to find the molarity of this solution of sodium hydroxide. Once we determine the concentration of sodium hydroxide, in week 2, we're going to use our sodium hydroxide to figure out the unknown concentration of some unknown acid and figure out the identity of some unknown acid. So week 1, we're accurately determining the concentration of sodium hydroxide using a titration. This is known as standardizing our sodium hydroxide. Okay, so how do we use a titration to determine the unknown concentration of sodium hydroxide? Well, we need to think about the chemical reaction that takes place when we start adding sodium hydroxide to our weak monoprotic acid. We'll call it HA. So a chemical reaction happens, as you're all aware of. Our weak acid will react with sodium hydroxide. Again, when we add sodium hydroxide to water, it's completely soluble. So it breaks up into Na plus and OH minus. The Na plus doesn't do anything in this reaction. It's a spectator ion. What's important is the OH minus. And the OH minus will combine with the H plus from our weak acid. Because the base is strong, this reaction goes 100% to completion. The OH minus and the H plus combine to make water. And we are left with A minus. So you remember from your lecture, if HA is a weak acid, A minus is a weak base. All right. So how can we use a titration to determine the unknown concentration of OH minus? Well, what we're going to do is we're going to make various solutions that we accurately weigh out KHP. So KHP is a solid, so we can determine an accurate mass of KHP. So we accurately know how much KHP we have down here. Okay, so that's an important step one. Step two is we're going to add to this solution an acid-base indicator. And this acid-base indicator is essentially going to change color at the end point of this titration. The acid-base indicator we're going to add is phenolphthalein. Not terribly important, but what's important is phenolphthalein will be clear when the solution is acidic, and as the pH goes up, as the solution becomes more basic, we're going to see a dramatic color change from clear to a faint pink. So we're going to use this color change as a way of determining when we have a really significant pH change down here. And we're going to use this clear to faint pink color change to determine the end point. We'll take that as the end point of the titration. So the end point is we're adding our sodium hydroxide, adding our sodium hydroxide. All of a sudden, when we see the solution go from a clear to a faint pink, and that faint pink persists, it stays around for, I don't know, 15 seconds or so, we will take that as the end point of our titration. Well, our end point is going to be a really good approximation, because we've designed this experiment appropriately, of the equivalence point of this reaction. So the end point is what we measure in the lab. The equivalence point becomes really important. What is the equivalence point of a reaction? Well, this reaction goes 100% to completion, right? And it tells us for every 1 mole of HA, it will react with 1 mole of OH minus. Well, the equivalence point is going to be, so this is something important you have to know, the equivalence point is the point at which our reactants are in their stoichiometric ratio. Meaning, for this particular reaction, the equivalence point is when the moles of our weak acid equal the moles of our strong base. So the equivalence point is when the moles of HA equal the moles of OH minus. Okay, and we know when the equivalence point happens based on the color change, based on the end point from our acid-base indicator. All right, so what will we know in this reaction? We'll know the mass of our weak acid, so we can calculate the moles just using the molar mass. We're going to record the volume of the NaOH added, so we are going to know accurately the volume of NaOH it takes to reach the equivalence point. Okay, so let's just briefly walk through these calculations. If we know the moles of KHP, we know at the equivalence point it equals the moles of NaOH. So we'll know the moles of NaOH in this reaction. If we then know the volume required to reach the equivalence point, we can find the molarity, because what's molarity? Moles divided by liters. All right, we're going to do this for 4 solutions. So Scott made a video, I'll post it on YouTube, just kind of showing you how to do this experiment. But we're going to do 4 titrations. The first one, we're not going to count towards our calculations. It's just a really fast titration, just so we know about how much it takes to reach the end point. Once we know about how much it takes, then for our other titrations, we can go fast in the beginning until we approach the end point. And then as we're approaching, then we can really go slowly and dial it back. So it actually saves quite a bit of time to do a really fast titration first, and then do 3 careful ones. So we'll have 3 data points we're going to perform calculations for. Okay, so we will have be able to find an average concentration of NaOH from these 3 sets of data. All right, So let's say we had the following. For example, also I will mention that I posted data for you guys to use for this lab report. I posted that on D2L as well. But let's just go through, I'm going to make up some numbers and let's go through a quick example of how we can do these calculations. So let's say, where did I do this? Here we go. Let's say we made a solution by dissolving 0.452 grams of KHP in the amount of distilled water that was required. Okay, let's say we originally started at a volume, so we record an initial volume of NaOH, and let's say our initial volume, let's say our burette started at 1.62 milliliters. We added the NaOH until we reached the end point, and let's say when we reached the end point, the final volume was 23.79 milliliters. From this data, we should be able to calculate the concentration of NaOH. All right, how do we do that? Well, we know the grams of KHP. We can look up the molar mass of KHP. So we can figure out the moles of KHP, which is 0.002213. I'll just keep a bunch of significant figures and round at the end. So we really are starting with 0.002133 moles of KHP down here. Okay, well, what is true? At the equivalence point, the moles of KHP equal the moles of NaOH. So if we started with this many moles of KHP, guess what? At the equivalence point, we must have the same number of moles of NaOH. So we know how many moles of NaOH we have. Sweet. So we know moles of NaOH because at the equivalence point, the moles are equal. All right. Did we want to figure out the moles of NaOH? No, we wanted the molarity. So how do we find the molarity of NaOH? You simply take the moles and divide it by the liters. Well, liters of what? Well, if we want the concentration of NaOH, we have to take the moles of NaOH, divide it by the volume of NaOH used. So how much NaOH did it take? Well, if the burette started at 1.62 and it ended at 23.79, we used a total, just subtract the two. The volume of NaOH used was 22, or should I write this? Just subtract the two. The volume used was 22.17 milliliters. Wonderful. Well, what's molarity? It's moles divided by liters. So the liters of NaOH I used is 0.02217 liters. 22.17 milliliters. So moles divided by liters will give us our molarity. So you should find from this data, we had a molarity of 0.0998 molar NaOH. Get out of the way. Okay, where did I get moles? We know the grams of KHP, so we know the moles of KHP. That's equal to the moles of NaOH at the equivalence point. So if it took 22.17 milliliters to reach the equivalence point, the molarity is simply moles divided by liters. Why did I round to 3 sig figs here? Well, what measurements did I make? I made a volume measurement, which really should have sig figs to the 100th of a milliliter, or 4 sig figs. But my other measurement was a mass of KHP, which I gave you to 3 sig figs. So my molarity should have 3 sig figs. Okay, so the data I gave you all on D2L is right here. So For each of our 4 runs, again, the fast titration, don't calculate a molarity. That's just approximate. But for run 1, 2, and 3, you should be able to take the grams of KHP and the molarity, the milliliters of NaOH it takes to reach the end point. You should be able to take these data to calculate molarity of NaOH. From this, you should be able to find an average, a standard deviation, all of that wonderful stuff. What we will do, we will then take this data and perform a second week experiment, which I'll make a new video for. Oh, you couldn't see any of that. Damn it. Okay, sorry. So here's our fast titration. Don't calculate molarity. Run 1, 2, and 3. I've given you grams, and I've given you volume of NaOH needed to reach the end point. So from these data, you can calculate molarities. Okay, that's it.